Now we are in chapter 1, Introduction to Digital Design. So these are what you will learn in chapter 1. Yeah, we will look at the overview of digital design. Next, we will look at the what we call philosophy of digital design. All right, there is a philosophy of digital design. We will see what is that. And we will look at the platform and tools that we will use to help us to design a digital system. And lastly, we will look at the what we call the implementation technology. Yeah, so it means that the design, our design, what is the technology that are available for us to be used to implement our design. All right. So first, look at the digital design. What is digital design actually, and why digital design? Because very simple answer. Because digital is the key to the future. All right. Because of digital, we have what we have today. Okay. If you look around, everything, almost everything is is able to be here because of digital. All right. Your handphone, the device that you carry almost 24 hours, even when you asleep, all right, your handphone is beside you, right? Even you go to toilet, your handphone is with you also, all right, almost 24 hour. Okay, so it is possible because of digital, and your handphone is a digital device. Yeah, the data that is used or processed in your mobile phone is digital data. All right, and now the second question is, what is digital design? All right, digital design is simply uh, when we build or customize a digital system from specification. That is digital design. Means that we have the specification and we design the digital system or digital circuit that used to process the digital data. That is digital design. Or in other words, build our own digital circuit rather than using a general purpose processor. This is very important. You need to be able to differentiate this. All right. But you need to understand, or you need to know, what is general purpose processor first. So what is general purpose processor? Anyone know this? Give Maybe you can give one example. What is general purpose processor? All right. Digital design is the process of designing a digital circuit or digital system to manipulate digital data. All right. Digital design is not uh, designing a circuit using general purpose processor. So what is general purpose processor? Right. To understand this term, we need to know what is general purpose processor first. So any one of you know what is general purpose processor? Anyone? Yes.
Processor computer.
Processor computer is general purpose processor. Yes, correct. All right. Means that we design not using uh, the circuit, not using the processor inside our micro computer, for example. All right. That is a simple answer lah. But I want you to look at this, right, so that you have better understanding. So hopefully you can see the screen here, right? I think most of you know what is Arduino, right?
Yes, sir.
Mm. So Arduino is general purpose processor actually, because Arduino can be used to do many things. So it is a uh, part of general purpose processor. All right. So for example, if you want to design a simple application, for example, you want to blink an LED. All right, make the LED on off in fixed interval. For example, every 1 second you want to on, you want to off, just to blink an LED. So what you will do is, normally you do this, right? You have the what we call the general purpose processor, which is your Arduino, right? Uh, so what you do is you just connect this Arduino to an LED, like this, and you write a program, a C program, to on and off the LED every 1 second, right? So in your program, you can write like this. And you have a delay for, you have a function delay that will give you a delay 1 second delay, right? And you off the LED, and you have delay for another 1 second, the same function, and this will end your program. Okay, so this is designing a simple application or electronic circuit using a general purpose processor, which is the Arduino. All right, this is not digital design. All right, so if we want to understand what is digital design is the process of designing everything here, including this, all right, using digital circuit. So means that we design everything, all right, not use the ready to use microprocessor like this. So digital design means we need to design even the delay function here using hardware, using digital circuit, right? So what we will do is, we may have something like this, a multiplexer, right? I don't know whether you know what is multiplexer or not, but we will learn in this chapter. Yeah? I hope that you were introduced to multiplexer already in digital electronic. We can have a multiplexer like this, and we have number 1 and number 0, and connect to the LED. And of course, the multiplexer, you will have the what we call the control signal, and this control signal is from the timer circuit. And of course, we need to design the timer circuit, yeah, the counter. All right, we will learn how to design the counter in chapter 4. Okay, and this counter circuit is clocked by external clock. All right, and this timer will give you this pulse. at the output here. All right. And the, uh, the the time for low is 1 second and the time for high is 1 second. All right, means that the period is 2 seconds, such that you can have on and off here, right? Because when here is low 0 for 1 second, all right, if 0 means that 0 here will, or this LED will receive 0, so this will off for 1 second. And if this is high, all right, high, logic high, so means that 1 will go to this LED and this will on the LED for 1 second, and so on. So this will blink the LED also. All right, but see, we're not using a program like this. Huh? All right, this one you just connect the Arduino to this and then write the program like this, and yes, you have the LED blinking. But this one, we need to design our multiplexer and we need to design our timer, all right, to give you the output like this, such that it will blink every 1 second. So that will be the design, and this is exactly what we will do in this course. And why this is important, right? It is because the performance, later on we will see, this circuit is much better in terms of performance as compared to this one. At least in term of cost, cost. You can see here, this one Arduino is a very complicated circuit inside. So if you want to just doing a very simple application like this, you will waste many resources. All right, you will waste many resources because most of the resources here you will never use. You just use for on and off LED. But this one, everything here is designed for this on and off LED. No resources are wasted. Everything is used, and the circuit is much smaller as compared to this one. This one, if you look at Arduino circuit, it is very complicated. And if you have very complicated circuit, of course, it will consume more power. Consume more power. So this one will consume less power because the circuit is small. All right, only the timer and very simple multiplexer. So power consumption, this one win. Right, in terms of cost, this one win. In terms of speed also, this one win actually. All right, because this one, because the circuit is big, all right, and this is optimized. This is actually not designed for this only this application. It is designed for many more application. It is multi-purpose. You can add anything that multi-purpose, you cannot get the best from it. All right, but this one is very specialized. All right, so again, everything that's specialized is the best. Okay, so that is why we learn digital design in electronic engineering. Means that you should be able to design a very good circuit, not only depend on other people's circuit. All right, because sometimes we want our design to be very good, and very specific for certain application. All right, and this is the answer. Okay, so this is the one that we will do the whole semester. Okay, let's see. Okay, so that is about the design. And before that, we need to know, this is just a revision actually. You should know this before because you are in year 3 already. So you need to know what is what we call analog quantities or analog values, right? So analog quantities is simply continuous values, or continuous quantity. Digital quantities have discrete set of values. Continuous value means that every point here, for example, this is your data, your signal. So you have value at every point of time. And in time here, time, you have every point, every value at every point. For example, here, between 1 and 2, you have 1.5, you have value. 2.5, you have value. Even 2.6, 2.7, or 2.61, 2.7111, you still have value. That is analog, right? But for digital, you will lose some values. Yeah? For example, here, 1.5 you don't have. 1 point something you don't have. You only have 1, you have 2, you have 3, 4, 5, 6, 7, and so on. All right. So this is, we call it discrete. All right. But you see the shape is still the same. Yeah. Still the same. Means the information is still there. All right. But of course, you lost some information. So in terms of quality, we can see that analog is actually better as compared to digital because you have the complete information rather than this one. This one, you actually lost some of the information. But for example, like music or voice, yeah. So actually, we can remove certain part, but still the information is still preserved, because actually our ear is not uh, mean to receive all the information. So you can remove some part and you can still hear the same uh, information or the same voice. So although you lost some information, but it is still, the information is still valid. So uh, we can see that by using digital, one thing is that you can reduce the size of the information, okay, because you remove some parts here. You see, that is the one of the advantage of digital. And what is digital system? This one is digital quantity or digital value. Now, what is digital system? Digital system is a circuit or a system that is used to process or manipulate the digital value. That's it. And analog system is, of course, is a device or circuit that is used to manipulate or process the analog system. So that is the difference between digital system and analog system. Uh, but why digital? Why we use digital nowadays? Most of time we use digital. But again, although we have many advantages of digital as compared to analog, but analog is still important, yeah, because uh, the world is analog. Yes, before you can get the data into analog digital domain, of course the data is still in analog. So at some point you need that analog system to process the data, and after that you convert that data into digital. And still, don't say that analog is not important. Analog is still important, all right, because the world is analog. Remember that, all right. But why the core, the inside, we use digital instead, right? Because of these advantages. All right, first thing is ease of design. Easy to design digital system as compared to analog. So if you learn signal and system already, all right, and you learn analog electronic, to design a system to process analog signal is not that easy, right? The mathematics is quite difficult. You have integration. All right, you need to do Fourier series. You need to do Fourier transform. All right, and to design an analog filter is not that easy, right? But digital, to design a digital circuit is relatively easy, yeah, as compared to digital system, because the mathematics is simple. We will see later. We will use most of the time is arithmetic. All right, no integration, no division, no integration, no differentiate, All right, no Fourier transform, no Z transform. Okay, so mostly we've been used arithmetic to process the digital signal. Ease of storage, easy to keep, to save, to store. All right, this is advantage number 2. Because the digital value or digital signal is represented in binary number, number 0 and number 1. So it is easy to store. All right, to keep number 0, to keep number 1 is very easy. You can represent that using a switch, right? Switch on means that logic 1, switch off means logic 0, and we can store that using flip-flop circuit. Later on we will see. All right, very easy to store digital information as compared to analog information. Analog information is very difficult to store. All right, the next one is the accuracy and precision are easier to maintain. This is related to this one and less affected by noise. Okay, so again, to understand this, we need to see this. So let's look at what is the difference between analog and digital value, right? So analog value is stored in term of voltage level, voltage. All right, this is how we store analog or represent the analog value. So when we transfer this, all right, or send this value or data into another device, so normally we will send using wire, right? We have a wire. So for example, you have two systems. So you will want to send the data from system number 1 to system number 2, right? So you will use a wire, and when you send the data, the analog voltage through wire, so most likely it will affected by what we call noise. So noise come from everywhere, all right, from the RF signal from outside, from the space, all right. So means that it is interfere with your signal here, because this wire is actually a good antenna, a conductor, so it will induce any signal that come from the from space, or any other electronic devices, will radiate the noise, to your system. So rather than you receive a very smooth, nice like this, so you may end up with the signal like this at the receiver end. All right, so that's why you can, if this is a sound signal, a voice, so you will hear uh, a noise signal, right? A burst signal, right? Because of this. But if we represent or we send digital data, all right, that different, because digital data is represented in binary number. For example, this voltage here, all right, for example, this is number 5, right? So we represent this number 5 by, for example, our system is 4-bit, so number 5 in binary is 0101. Okay, and of course we still transmit the voltage. So but in digital it is transmitted like this: 0 1 0 1. right? So this is 0, 1, 0, 1, which is 5. 0, 1, 0, 1, which is 5. Okay, and we send this, and the question is it affected by noise? Yes, it is affected by noise because this one is electrical voltage. Of course, it is affected by noise, but at the end, we have something like this. Okay, and we can see that this one still 0. The receiver end still recognize this as 0, and this one is still 1. This one is still 0. This one is still 1. So although you have noise along the way, but it is easily recognizable as 0 or 1, all right, for digital signal. So that is why we say that accuracy in precision are easier to maintain, yeah, and of course less affected by noise. uh, Programmable operation. So uh, the digital system is easier to be programmed, or we can use, or we can program the digital system as compared to analog system. This is means by uh, this. Programming in electronic is something like this. Although we write the program in our computer, it's actually translated to digital representation or digital data. Yeah. So for example, you write the code on your computer. Actually, it is translated to 10101010, something like this. So this is digital data, and this one is actually used to control your circuit to do something. Input, output. This we mean by program. Yeah, this we mean by program. So it is easy to program digital system as compared to analog system. Analog system is very hard to program. All right. So you can see that nowadays when we program, almost all our programming uh, that we use is for controlling the digital system, digital circuit, not analog circuit. Okay, ease of fabrication on IC chips. Okay, so again, digital system is easy to fabricate, to make the IC for digital circuit as compared to making the IC for analog circuit. Why? Because digital system is comprises of or mean to process digital signal. So digital signal is, we know already, we have 0 and 1. So to represent 0 and 1 is easy in electronic. We use transistor, all right, because transistor can be used as a switch, all right. So switch, again, switch on means logic 1, switch off means logic 0. So we mainly use transistor to represent digital value, and to fabricate transistor is very easy, all right. It's easy on semiconductor, yeah. You will learn in detail in year 4 how we fabricate the IC, right? But here now you should know that to fabricate the transistor is relatively easy as compared to fabricate the analog component or device. Analog device, for example, is capacitor, inductor, resistor. That is very difficult to be fabricated on semiconductor. For example, inductor, which is quite tricky to design or to fabricate on that. But transistor is quite easy. All right. So that is mean by ease of fabrication on the IC chips. Okay. So that is some of advantages. There are actually more. All right. Advantages of digital system. So you should understand this. Why is it important and why we learn this? Okay. Now we know already what is digital system, what is digital design, and why we learn digital design, why we use digital. All right. And now we will look at how we design. Okay. So this one we call design domain. Design domain. So design domain is view by this chart, or can be represented by this chart. This chart is called a Y chart. If you go to Google and search for Y chart, so it will give you this. Or other name is actually called Kun-Gaski chart, which is actually introduced by that guy, Kun-Gaski. All right. So if you search on Google, KUHN Gaski, so this is the this Kun-Gaski chart. So there are a lot of this. So this is oops, sorry. So this chart is for representing what is design domain that we have in modern design, digital design. So we have mainly 3 design domain. We call it behavioral domain, structural domain, and geometrical or physical domain. All right. So what is the difference between these 3 domain? Behavioral domain is mainly used to describe the digital circuit using its behavior. All right, the behavior of the circuit. For example, Boolean equation. Boolean equation is the behavior. For example, C equal to A or B. So that is the behavior of the circuit. Means that the output of that circuit is A or B. All right, with the behavior. But the structural model domain, we're not designing using behavior. We're not designing using uh, equation. It is the structure of the circuit, which is the lowest level will be the transistor circuit. All right. So just now I said the digital circuit is represented by transistor. So of course we have transistor. Okay. So here we see that this is the bottom of the design what we call design hierarchy. All right. So this is the top of the design hierarchy. So for example, in behavioral domain, so we can look at the lowest one is the Boolean equation. The next one is module description. Module description means that we have the module, all right, and we describe how is its work, is its works. For example, the adder, all right, the adder inside there is the logic. So the adder we can write the description is the output F, for example, is equal to A plus B. A plus B, that is behavior of that module, adder module, A plus B. Or finite state machine, finite state machine. All right, we learn in chapter 4 the state diagram when we is represent the behavior of the circuit also. And of course, the algorithm, algorithm representing the behavior also. And in the structural domain, we will not looking at the behavior, but we look at the structure of the circuit. For example, how this transistor connected to the next transistor and connect to the other transistor. That is structure. Leaf cell means that the gate, you can view that as a gate. For example, gate A connected to gate B, connected to gate C, and you get the output. Or maybe higher than gate level is the register level. We will see in chapter 5. All right. And the highest level is the processor level. We will look at this in chapter 6. Right. And the last domain is the physical domain. So physical domain is the actual uh, structure or actual circuit on the silicon, on the chip, right? So it is the real chip. All right. So just like you design a circuit using on the printed circuit board, PCB, right? So you need to have schematic, right? So the schematic is actually in the structural domain. All right. Schematic is not the actual circuit that you want to create. Schematic is just a visual description of your circuit, how this point is connected to this point, right? But the actual connection is on your circuit is the mask, that you want to print on your circuit board. So same as this one. This is the mask that you want to print on the silicon chip. All right. How the same cell is placement. This module is placed here, and placed here. The actual one, right? Until you get the chip. We call it floor plan. And the whole chip, the whole IC. All right. So for your information, our course will focus on these two domain, not this one. This one will be covered in another course, which we call VLSI course. All right. But these two domain, behavioral and structural domain, will be covered in our course. All right. We will look at behavior of the design, or we will design our circuit based on behavior, and also we will design our circuit based on the structure, depending on what kind of circuit we want to design later on. All right. Okay, so this one is discussed already here. All right, same thing. So you can go back and try to read this. Same thing. Right, next we will look at this philosophy of digital design. So we have 4 principles to achieve the design effectively and quickly. So how to design the circuit basically. So you must think everything that, for example, we have many circuit nowadays. We have digital circuit in our phone, in our computer, in our smartwatch, everywhere, right? So you might be wonder how people or how engineer design the circuit to do uh, just like that, yeah, just the application that we can see now. All right, can run Windows, can run Android. The circuit must be complicated, right? And we heard that, we know that when we read from the internet, the microprocessor that is the core of that circuit, uh, we read that the number of transistor inside that microprocessor is billion nowadays, million, billion of number, billion of transistor. How do people or how do engineer design a circuit that consists of billion of transistor? Wow, that is very difficult, right? So the key is the engineer is not designing one transistor by one transistor. If not, there will be no complicated circuit, complex circuit that we can see. So there is a method to do that. All right. How we achieve such a very big design, all right, in a short time. Okay, so there is a way. So the way is what we will, that way, that method is what we will learn in this course. Yeah, and it is comprised of comprises of these four principles. The first one is called hierarchy, second one is regularity, third one is modularity, and the last one is locality. Let's look at the first one, hierarchy. So what is hierarchy? Hierarchy means that if we look at organization, right? So we can see that the hierarchy means that we have the bottom, we have the next level until the top level, right? So that is hierarchy, means that it is divided into division, and each division support the top level, right? So normally when we want to design the circuit, a complex circuit, we're not designing the whole circuit at once. All right, means that from from zero to the complex circuit, you cannot do that. Huh? That is that is very that is impossible to do that. So what we do is we divide, yeah, the that big circuit, that complex circuit, into a smaller component. All right, and we design its components separately and combine together to get the complete design. That is meant by hierarchy. For example, if we want to design an ALU, ALU is arithmetic logic unit, where you need to design in this course, of course. So for example, we want to design an ALU, and an ALU is a very useful circuit. It is used in every computer, every handphone that you have, every smartwatch that you have, every uh, uh, any device that need computation. eh? So you need to have ALU. So for example, we want to design an ALU. All right. So the ALU is quite big circuit. So we cannot design. Okay, I want to design ALU. I start with Boolean equation, and this is ALU. No, which is very difficult. So what we do is we need to have we need to know ALU comprises of what component. All right, so we have multiplexer, we have adder, subtractor, we have logic, we have multiplier, or we have may may have any other module, division module, divide, for example. So, and again, the multiplexer is comprises of many logic. All right, adder and subtractor, we have adder circuit inside, to build the adder, to build the subtractor, and of course the lower level is the logic. And logic, of course, we can design straight away. Multiplier is actually comprises of many adders, and we add together and we get multiplier. And all of this we combine together, we connect each other, we get the ALU, the big circuit. So this is called hierarchy design methodology, right? So we call it divide and conquer. Yeah, we divide to a smaller module, design in smaller module before we combine to get a bigger module, right? And the second one is called regularity. What is regularity? Regularity is very important also to get a very big circuit. For example, we want to design an adder, all right? So because of regularity, we can design a 1-bit adder and combine that 1 bit together using the same one. All right, so this is the same circuit. This is the same circuit, and connect this way, so we get the 4-bit adder circuit. Or if we want to get an 8-bit circuit, so we just extend the number of adder here using the same design. All right, you can see that the design is from less complicated, we can get a very complicated circuit by using regularity method. All right, we use again, means that we reuse our design. Or maybe we want to design another example is memory. Yeah, memory is comprises of uh, many many similar or the same block of circuit. All right, so for example, you have 1 million byte of memory, right? So actually every byte that you want to store, the circuit that to store that every byte is the same. The first one, the second one, until the 1 million byte is the same circuit. So you can use repeatedly. All right. So for example, if 1 bit you need 10 transistor already to keep, or one transistor to keep 1 bit, for example, just for example. So if 8 bit, you have 8 transistor. All right. So if 1 million byte, so you just multiply 8 to 1 million. So you have 8 million transistor already. That's why you see, although you have, uh, you see that, oh, million or billion of transistor. How do people do that? Actually, it is this way, because the design is repeated. All right, most of the time. So we can get the big circuit from the small circuit. And next is modularity. Modularity is actually not uh, covered in our course. Our course is looking at regularity and hierarchy. Hierarchy. This is covered in VLSI course, but you need to be introduced to this. Modularity is when we design in our circuit in module, so we need to make sure that our circuit can be interfaced with other circuit, right? So for example, again, when we want to design the ALU like this, in lower level, for example, the mux here, when we design the mux, the multiplexer, we need to be able to, we need to make sure that the uh, signal, the connection between this one can be interfaced with this one. All right. If not, it will not function. Okay. So that is mean by modularity. So means that uh, our circuit can be used or can be interfaced with other module in the system. And the last one is locality. Locality also is studied in detail in VLSI course, because this is more on physical design uh, issue, where we when we design a module, a circuit, we need to make sure that any optimization that we want to make in the module will not affect the the other module performance. All right. So for example, we want to reduce the power consumption of our module. So we need to make sure that when we reduce the power consumption of this module, we will not affect power consumption of other module. So that is locality. Means that everything that we do in our module, not affect our the neighboring module. All right. So that is locality. So again, go back to this. So we have 4 principles, but we will focus on hierarchy and regularity in our course. This one will be in the VLSI course. Okay, so now look at the tools and platform that we will use. Again, just like I said before, because we want to design the complex circuit, so we need a tools to assist, to help us to do that. In our case, we need a computer, all right, to help us to synthesize the circuit that we want. So we will describe or design our circuit using hardware description language, where this language will help us to design a complex circuit. And to generate the circuit, the computer will do the job for us. Yeah, that's why we need the tools. Right. But although we have the tools, yeah, so it's supposed to be easy, right? Because we just uh, describe our circuit based on the specification, right? Described like this. But why why we have the tools, but why we need to learn the theory behind? Why we need to know the theory? Why we need to learn the concept? Why we need to learn how to design, how to get the best or optimize, or why we need to learn how to design a good circuit if we have the tools to do the job for us? So this is why. There are three big reasons for learning the relevant theory. First, although the CAD tool perform the automatic task most of the time of optimizing the logic circuit. For example, you just give the computer the equation, and most of the expensive modern tools can do the optimization. Means that to minimize the circuit for you, give you less power, and so on and so forth. But uh, the designer has to give the original description. Means that the designer or engineer need to know exactly, if I do this, what I will get at the end of the day. All right. If the designer specify a circuit that has inherently bad properties, for example, you are an engineer, but you have bad knowledge. You have no knowledge, to design a good circuit. So you may give the bad properties, bad specification to the computer. All right. Then the final circuit will also be of poor quality. All right. This is normal. If you give bad input, you receive bad output. That is why. So if you are a good engineer, you know everything, so you know exactly what you do, right? That is why. Number one. Number two, the algebraic rules and theorem for design and manipulation of logic circuit are directly implemented in today's CAD tool. Yes, you give the finite Boolean equation, the CAD tool can generate the circuit for you. That's no problem. It is not possible for user of the tool to understand what the tool do without grasping the underlying theory. So again, this is related to the first one. So if you are the an engineer, right, to design the digital circuit, you just give the equation to the computer and lets the computer do that. Actually, you have no idea what the computer do. All right. Sometime the we will see in chapter 6, where when we learn how to optimize the algorithm. Sometimes the computer will not give you the best solution. So you as an engineer need to do some tricks, some tricks and or modification in order to get full uh, output or full uh, outcome from the computer. Right? We will see later on in chapter 6. Right? That is number 2. Number 3, CAD tools offer many optional processing steps that a user can invoke and working on design. Yes, we will see later in our tools that we can use many features that we can call, or what we call invoke, when we design. The designer can know whether it meets the required objective. The only way that the designer can know whether or not to apply a particular option, this is very important, in a given situation, is to know what the CAD tool will do if that option is invoked again. Yes, so we will see that in our tools later on in our software, we will have many options. So as an engineer, as a designer, we need to know exactly, if we use this option combined with this option, for example, what is the output. If we know the theory, if we have a strong fundamental knowledge, then we can create a good circuit by using the software. So again, this implies that the designer must be familiar with the underlying theory. So This is why you need to know the theory that we learn in this course in order to be a good electronic engineer or designer, right? Now let's look at what is the tools that available for this. So this is generally what we have nowadays. So you need a personal computer, a laptop, and of course you have your laptop, and then you will need to have a software where you can download from the internet, and there is a free license that can be used for our course, and of course there is the license one, but you need to pay. But for a design in our course, the free license is actually uh, enough, sufficient for the course already, for our design already. And we need the device, the device. So this is the hardware. So we actually don't need this in our class. So we will do the simulation in the software. All right, is sufficient already to understand what is the content of the course. All right, and all of these are the hardware. Yeah. So we will basically have our computer, and the software is enough already for this course. All right, now the last one is the implementation technology. So implement technology is just like what I said before in the introduction, is where or the target of our design. So we have our design, so we want to implement our design whether we want to use the what we call the standard chip or programmable logic devices, or what we call the custom design. So standard chip is this. Actually, this is phased out already. But I think you have learned or used this IC before in your previous course, digital electronic, where you have, for example, this IC 7404 is the NOT gate, where you can use to connect to other IC, for example 7408, like this, to implement or to realize this equation, and you get path here from the input x1, x2, x3. So that is called standard chip, and this one is actually phased out already. But for education, is yes, we still use in education to help you understand what is going on. But in practice, this one is never used already. Phased out. Then the second one is programmable logic devices. Programmable logic devices is popular until today, and this is good for prototyping, because we can create our design fast, very fast. Once you have the design, you can implement your design already. You can test your design already in the hardware already. All right, and this is programmable, means that you can change the design and reprogram the chip to give you the output that you want. All right, that is called programmable logic devices, and the one that we will use in our course is this one, FPGA. We will see later. And the last one is custom design chip. What is custom design chip? Custom design chip is the chip that is used in your PC, in your handphone. All right, for example, the microprocessor is actually come from the full custom and semi-custom design. Means that it is fixed already. It is fixed already, and then it is printed on the silicon chip already. So when you look at the chip, so that is the semi-custom or full custom design chip. Right. This one is expensive. You need a very big factory. For example, Intel in Malaysia, not Altera, sorry, Silterra. Yeah, to fabricate the chip. So means that you have the design and you want to fabricate on the semiconductor on chip. All right, so that is called full custom design, or full custom chip. Okay, so in our case, yes, of course we design the circuit, but we will implement on the programmable logic devices, where we can program and reprogram many times. All right, when we change our design, we can have the new circuit very fast. So normally people use this for prototyping to test the design. All right, to test the design first, and if everything is work fine, work good, and the next step is to have the full custom design, because this one will give you the best performance, the best performance. But of course, it is expensive. Okay, so in our case, we learn how to design and not to create or fabricate the chip. So this one is not in our focus. This one is for VLSI class in advanced or next class. Right. So look at the programmable logic devices that we have today. Okay, the first one is called PLD, programmable logic device, introduced mm, in the 1970s, very long time ago, 50 years ago, right? Uh, General purpose chip for implementing logic circuit, contain collection of logic circuit element that can be customized in different way. This is the key. Contain logic element that we can customize in different way. It means that we program. Okay, so for example, we give input, we customize this based on our specification, and we get the output. So for example, the first PLD is called the PLA, programmable logic array. Yeah, contain of what we call the N and O plane, like this. Yeah, this is called an N plane, and this is called an O plane. Yeah, so we have what we call the programmable connection or programmable switches here, where we can connect and reconnect based on what we want to implement. For example, we want to implement uh, this this f1 is equal to in this example, we see that f1 we have how many connection we have. Input we have 4, but only 3 of them are connected. P4 is not connected. All right, means that we not connect here, and here we connect. All right, so meaning that if we look at this, right, okay, we are at 11:01. I think we need a short break, 5 minutes maybe. Before that, any question so far? I think we should manage to finish all this by today, which is good progress. And the class is recorded, yeah, so that you can always refer back, do the revision. All right. So any question?
So far, no, Doctor.
Okay, good. Either good or bad, right? No, no question at all is either good or bad. Whether you are uh, you fully concentrate or you lost at all.
Yes, fully good.
Okay, hopefully
50-50, Doctor. 50-50.
50-50. Okay, uh, it's okay. That's normal actually. So you can ask me anytime through telegram, or maybe author, or maybe you can direct message uh, regarding our class, our course. So I will try to get back to you as soon as possible. Not, don't expect me to immediately reply to your message, because I I have other thing to do. All right. So I sometime maybe reply you quite late, but I try to reply. I try to answer all the questions. Okay, so we have maybe 5 minutes break. Come back at 11:08. Okay.